Hi, my name is Andrew Buck. I'm from the University of Missouri, and today I'll be presenting our paper for FUZZ IEEE 2021 called A Fuzzy Spatial Relationship Graph for Point Clouds Using Bounding Boxes. So this paper is really all about 3D scenes and how to represent the content of 3D scenes. In particular, um, raw point clouds, whether they're captured from LiDAR sensors or from a depth camera, contain a lot of information, and these files can just be massively huge. Um, what we'd really like to do is be able to understand those scenes, identify objects through semantic segmentation, and then understand how those objects relate to one another spatially. So one of the ways that we can do that is using simulation, just to capture a simulated environment so that we know exactly where these objects are. And so we don't have to worry about the semantic segmentation part. We can focus only on the idea of what is the spatial relationships between objects in a 3D scene. And that's really the focus of the talk today. So this actually has a lot of interesting applications. First of all, we'd always like our AI systems to have an interpretable understanding of the environment so they actually know a little bit more about what they're doing. That can help make them a little bit more human-like and easier to communicate and um, use natural language to explain what you'd like the robot to do. And it also helps reduce computational overhead. So these small embedded systems typically can't handle large point clouds. And so having a simplified representation of that helps them understand the content of a scene can be really important. So the data set that I'm going to be using to explain most of this today is well-known data set, the NPM 3D benchmarks suite. And this data set is really nice because it's got hand-labeled uh, ground truth segmentation. So for every point, we have a class label and an instance ID. So we know that, for instance, it's not just a point belonging to a person, but a specific person. And so this lets us create our object representation of the scene. And in particular, we're going to look at just a small section of this data set where we've got about 10 million points and 100 labeled objects. So the question that we want to ask is, can we compute the spatial relationships between these objects? So if we were to draw a bounding box around every one of the labeled objects in this scene, could we compute the spatial relationships between those objects and then use that for interesting things? So first of all, let's focus on just two objects. So if we consider these two objects here, um, you can see we've got a signpost and a lamppost. In 3D, we've drawn a bounding box around these objects in all three dimensions, and we've also labeled a centroid. And so if we do that, we can actually compute triangular fuzzy numbers to represent the positions of these objects in 3D space. So the triangular fuzzy number has a minimum point and a maximum point defined by the bounding box, and then the peak of the fuzzy number is defined by the centroid. And so this lets us represent the position of a 3D object with just 9 values, 3 values for each dimension. So a reasonable question then is, what is the distance between objects? So one way we can do this is to look at each dimension individually and then compute what is the difference between these two triangular fuzzy numbers. So for instance, in the x dimension, we have a triangular fuzzy number for the position of object A on the x-axis and position of object B on the x-axis. If we subtract these two using fuzzy arithmetic, we get a new value that is the difference between A and B in the x dimension. And we can repeat that for x, y, and z and get three new triangular fuzzy numbers that represent the difference between these two objects in each dimension. So now, once we have that, we can compute an overall distance just by using the Euclidean norm. So we square each dimension, add them together, and then take the square root. And that gives us an overall distance triangular fuzzy number, where the minimum value here represents the minimum possible distance between these two objects. The maximum value represents the maximum distance from one corner to another, and then the peak value is the distance between the centroids. So what can we do with this? Well, one thing we could do is we could start to build up a spatial relationship graph where we connect objects that are close to one another. So then we have to have some sense of, are these two objects close enough to each other to put an edge between them in this graph? And so we have to have some way of defuzzifying a fuzzy number, for instance, with some threshold, say d. So for instance, is d less than 10? Maybe, maybe not. So what we can do is we can define a parameter that we vary between 0 and 1, and we basically interpolate to define where we're going to consider that triangular fuzzy number to be as a crisp value. So when the value is low, when it's 0, we pick the minimum. When it's high, we pick the maximum. When it's 0.5, we pick the average. And so when this value is high, what we end up doing is we interpret the distances to be very large, and we end up doing something like complete linkage clustering. So if we were to draw the distances between all the objects in the scene, we would get these compact clusters where our threshold here is 10 meters. So if we decrease this parameter, we start to get a little bit more connection. So the distances are being interpreted to be a little bit shorter. And as we continue to decrease, we get more and more connections. And as we go all the way down, anything that is within 10 meters of another object is going to get an edge. And so we're going to get lots and lots and lots of edges in this graph. It's kind of like single linkage clustering at that point. Okay, so now we could actually use that to do some type of distance query. So perhaps we want to find all the objects in the scene that are a certain distance away from a given reference object. So we could define a query distance with another triangular fuzzy number, and then determine what is the similarity of these two fuzzy numbers, so the distance value and the query distance. So we can look at the intersecting points of these two triangular fuzzy numbers, take the maximum value, and call that the distance similarity. And so that would be a value between 0 and 1 that says how similar is a particular distance to this query distance. So here are a couple examples. We're looking at a person in this scene outlined with a red box. In this first case here, we're looking at a query distance of 0, 0, 1. So the distances have to be completely less than 1 meter in this case away from this person. So we see in this heat map just about nothing is lit up except the person itself. And as we start to increase this value, so we go from 5, 10, 15, we start to highlight things a little bit further away from that person. And as we increase it a little bit more, we start to get things even further away, and we start to exclude the things that are right on top of this person. And then far off, we only really highlight things that are really far away. And so we have a lot of flexibility in how we might define how far away objects are from a particular reference object. So the next question is, how might we define the direction between two objects? So these difference values, this dx, dy, dz, the difference triangular numbers in each dimension, they encode both the distance between those objects, but also the direction between them. So what we can actually do is think about it in just 2 dimensions to make it a little easier to understand. If we take 2 objects, say A and B, and we compute the difference between them, we end up with this green object here. And so this represents the minimum distance in x, which would be 0.5. You can see here is 0.5 here. The maximum distance would be 2.5 from the minimum to the maximum. And we end up with this vector DAB that represents the difference between these 2 objects. Now if we normalize this down to a unit vector, so we take the maximum of these corner points and make that maximum value 1, we'll end up with a normalized version of this. And we can now take that normalized version of the direction and take the dot product of that with a reference direction, so u hat, which is a normalized unit vector. And so if we do that, we'll end up with a similarity value that's a triangular fuzzy number that ranges between -1 and +1, depending on how similar that direction is to our query direction. So to make it all positive and fit within our framework of 0 to 1, we can just clip it to a value of 0 and say anything greater than 0 is what we'll keep, and anything less than 0 we'll just clip it to 0. Okay, so here's a couple examples here where we're looking at direction. So if we said strictly to the north, we might only select objects that are the north direction of our reference object. And if we say to the southeast, so we change this query direction, we're looking at objects now in a different direction. And generally to the northeast, we can use this defuzzification parameter, this interpolation point, to specify how specific we want to be, saying strictly to the north or generally in that direction. And you can see here, even going above the object, you can start to identify things like the lamppost, which isn't strictly above the person, but is generally above that person. Okay, so all this comes together into a nice multi-criteria framework, so we can take things like the distance and the direction as features that we use to identify objects that satisfy certain objectives or criteria. We can use a scalarization function such as the average or the minimum to aggregate all of these different features together and pick an object that best satisfies multiple criteria. So here's an example of that, where we want to select, for instance, a lamp post that is both near and to the front left. So if we look at just the lamp posts near this object, so we can filter by object type, these values on top show the similarity scores of the distance query 0, 5, 10, so no more than 10 meters away, and a centroid, so a mean distance of 5 meters away. How well do each of these lampposts satisfy that? And then same with the direction. We can have a particular reference direction and defuzzification term that says how well do each of these lampposts satisfy that particular direction. So all of the ones out in front of the person kind of have a high value, and then the one behind the person has a very low value. And when we combine these using our min operator as the aggregation function, we see that just this one here satisfies our query of near and to the front left. So here's a bit more general case. So we might want to have a robot that's exploring the environment and wants to choose its next exploration target. So it wants something that's not too far away, in the forward direction, and also near the edge of the explored space. So we can start to include other criteria that might not be strictly distance or direction. And if we combine all of these together, we can start to get some kind of sense of what is the best object that you would want to use as your next destination target, the thing that you would want to explore next. So this is kind of a nice little framework that we can use to combine things like distance and direction in choosing objects of interest in a 3D scene. So to wrap things up, this is kind of a basic foundation framework for doing distance and directional computations in 3D space using bounding boxes, axis-aligned bounding boxes in particular. So one of the things that we haven't done is looked at if we were to use oriented bounding boxes to see how much of an impact having the axis alignment really makes on this, because there's obviously a lot of simplifications and cases that don't work very well for axis-aligned objects. However, there are ways around this, things like breaking up large objects into smaller objects, doing things like starting to understand how the graph should change over time as you increment the size of things. These are things that we're going to be looking at going forward. But ultimately, this is kind of a nice little framework, a way to compute these spatial relationships without the overhead of actually using more complicated methods on the raw point cloud data. So we hope to make use of this in the future going forward, integrating it with actual semantic segmentation algorithms to get ground truth, and that's basically it for this talk. So thanks for listening. Thanks.